To understand the observable universe, we must first travel back in time, approximately 13.8 billion years. It was an instant of incredible energy, a singularity, where current laws of physics collapse under extreme conditions. This event, the Big Bang, not only gave birth to the universe but set into motion the expansion that continues to this day. The universe we know today, a vast expanse of galaxies, stars, and unimaginable distances, was born from this moment. But what does observable really mean? It refers to the portion of the universe that we can see, given the finite speed of light and the age of the universe. As we peer into the night sky, the light from distant stars and galaxies travels billions of years to reach us. When we gaze at these celestial objects, we are, in essence, looking into the past. The farther away a galaxy is, the older the light we see. Did you know that the observable universe measures about 93 billion light-years in diameter? This measurement underscores the vastness of our cosmos, yet it also raises profound questions about what lies beyond this observable horizon. If space is infinite, which many cosmologists believe, then there exists an unimaginably larger universe just beyond our view. From the early observations by astronomer Edwin Hubble in the 1920s, who discovered that galaxies are receding from us, to the establishment of the cosmic microwave background radiation as evidence of the Big Bang, the narrative of our universe is one of relentless exploration. Hubble found that distant galaxies moved faster, a phenomenon now known as redshift, indicating an expanding universe. This expansion further leads us to ponder what lies beyond the limits of what we can currently observe. Through the decades, scientists have sought to understand the nature of this vast cosmos and the implications of its infinite nature. We have made incredible strides in technology, leading to remarkable discoveries, such as the detection of exoplanets and the study of cosmic phenomena like dark matter. Yet, the edge of the observable universe remains a tantalizing enigma. What pathways lie beyond this horizon? As we delve deeper into cosmic exploration, theories abound. Some suggest that the universe could be part of a larger multiverse, where numerous other universes exist alongside ours, each with different physical laws. The possibilities are overwhelming, and with every technological advancement, we inch closer to answering these cosmic questions. But how do we measure distances in this vast, expanding universe? This sets the stage for our next chapter. Measuring the universe is no small feat. From ancient astronomy to modern astrophysics, the methods of measuring cosmic distances have evolved dramatically. In ancient times, astronomers relied on simple observations and measurements. The Greeks, for example, devised early methods to estimate the distances to celestial bodies, but these were often rudimentary and inaccurate. With advancements in technology, our understanding has expanded exponentially. Today, astronomers use several techniques to gauge the vast distances in space. One of the primary methods is parallax, which involves observing nearby stars from different positions of Earth's orbit. By measuring the apparent shift in position against distant backgrounds, astronomers can compute the distance to nearby stars with impressive accuracy. However, as we extend our gaze beyond local stars, parallax becomes less effective due to the immense distances involved. For farther distances, we turn to standard candles like Cepheid variable stars and type Ia supernovae. These celestial phenomena have a known intrinsic brightness, allowing astronomers to calculate their distance based on how dim they appear from Earth. The discovery of the relationship between the period of a Cepheid star's brightness and its luminosity was a turning point in our ability to measure cosmic distances. Edwin Hubble's work built on this, providing essential data that further established the expanding universe theory. The latest advancements come from the use of redshift measurements. When light from distant galaxies shifts toward the red end of the spectrum, it indicates that they're moving away from us, a phenomenon directly linked to the expansion of the universe. This redshift gives us the scale and combined with the cosmic microwave background radiation data, helps us map the large-scale structure of the universe. However, as we push farther out into the cosmos, we encounter challenges. The universe is not a uniform place. Gravitational forces from massive structures can warp space and time, complicating our measurements. Therefore, scientists continually refine existing theories and techniques, leading to even greater precision in mapping the cosmos. But what about those distant galaxies that are beyond our current observational horizon? This question highlights the limitations of our technology and understanding. If the universe is expanding faster than the speed of light in certain regions, how can we ever hope to see what's beyond that limit? This dilemma opens doors to fascinating discussions about the very fabric of spacetime and leads us to our next exploration of cosmic mysteries. As we delve deeper into the nature of our universe, we encounter the cosmic microwave background radiation, or CMB, one of the most profound discoveries in modern astrophysics. This faint glow pervades the universe, emanating from every direction in the sky. It is a relic of the Big Bang, providing a snapshot of the universe when it was just about 380,000 years old, a time when it transitioned from an opaque hot plasma to a transparent state, allowing light to travel freely. The CMB was first detected accidentally by Arno Penzias and Robert Wilson in 1965. Their discovery earned them the Nobel Prize in Physics in 1978. Initially, they could not pinpoint the source of the background noise that disrupted their satellite communications. After ruling out various possible sources, they concluded that they had stumbled upon a phenomenon that would change our understanding of the universe. The CMB is not just background noise. It holds critical information about the early universe, with tiny temperature fluctuations that correspond to the seed density of the galaxies we see today. By studying this radiation through missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, scientists have been able to piece together the history of the universe and confirm key cosmological parameters, such as its age, composition, and rate of expansion. One of the most astonishing findings from the CMB is confirmation of the inflationary model, the theory that the universe underwent a rapid expansion just after the Big Bang. This model helps explain the uniformity of the CMB across the sky, despite the vast distances involved. Yet, as we analyze these patterns, we start to wonder what else lies beyond this early observable footprint. The CMB also raises questions. If we can detect the remnants of the Big Bang, then what about other potential signals from beyond the observable universe? Are there regions of space where conditions differ dramatically from our understanding? With cosmic inflation, the universe's size could be much larger than what we can see, perhaps even infinite. Our understanding of this background radiation invites speculation and curiosity about potential anomalies hiding just out of sight. As we unravel the mysteries of the CMB, we find ourselves drawn into new theories and untold stories of the universe, stories of dark matter, dark energy, and the structure of the cosmos. As we journey further, the next chapter will dive into these unseen forces that shape the universe in ways we are just beginning to understand. Have you ever noticed how most of the universe seems to be invisible? Yes, we are talking about dark matter and dark energy, two mysterious components that make up about 95% of the total mass-energy content of the universe. Dark matter is an unseen force that doesn't interact with electromagnetic forces, making it invisible to our conventional observational techniques. We know it exists because of its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Early evidence came from the rotation curves of galaxies, where astronomers observed that stars at the edges of galaxies were rotating at much higher speeds than predicted based on the observable mass. Without dark matter, galaxies would fly apart. But if it's everywhere, what exactly is it? This question baffles astronomers. Various particles, like WIMPs, weakly interacting massive particles, have been proposed, but no definitive evidence has yet been found. On the other hand, dark energy drives the accelerated expansion of the universe. First discovered in 1998 through observations of distant supernovae, it was determined that the universe's expansion was not slowing down as previously thought, it was increasing due to this mysterious energy that counteracts gravity. Together, dark matter and dark energy set the stage for an exhilarating cosmic drama, shaping the universe's fate. Yet, they also deepen the mystery of what lies beyond the observable universe. How do these forces interact with the universe beyond our view? What would happen if the balance shifted? It leads to questions about the end state of the universe and whether the very fabric of reality is malleable. Many experts theorize potential scenarios about the universe's future. Will it continue to expand forever, leading to a cold, dark fate? Or could it ultimately collapse in a big crunch? Understanding the roles of dark matter and dark energy not only reshapes our view of the universe but also our existence within it, hinting at a universe far more complex than previously imagined. As we reach the limits of knowledge in this area, our journey continues into the philosophical implications of what lies beyond the edge of our understanding. As we explore the vastness of the universe, the hope of finding extraterrestrial life beckons us forward. The search for alien civilizations has captivated humanity for decades, driving missions and technologies to probe the depths of space. Could we be alone in this expansive cosmos, or is life thriving in forms we can hardly imagine? Projects like SETI, the search for extraterrestrial intelligence, have been scanning the skies for signals from other intelligent beings. With powerful radios and telescopes, scientists analyze data for patterns or anomalies that hint at extraterrestrial communication. While we haven't found definitive evidence of alien life, recent discoveries of exoplanets in habitable zones around stars like our Sun have ignited excitement. The Kepler Space Telescope, launched in 2009, alone identified over 2,300 confirmed exoplanets, some within the Goldilocks zone, areas where conditions might support liquid water, a crucial element for life as we know it. Moreover, the discovery of extremophiles on Earth, organisms that thrive in extreme conditions like volcanic vents or deep-sea trenches, expands our understanding of potential life forms elsewhere. These findings suggest that if life can exist in extreme environments on our planet, it may also thrive in the harsh conditions of other worlds. But what if we do find a signal? What would be our response? The answers are as complex as the question itself, linked deeply with our philosophical and ethical beliefs. The idea of contacting advanced civilizations raises questions about the risks and implications involved. As we seek answers in our universe, we cannot ignore that we are looking at the universe's past while questioning the future. Beyond the observable universe could lie realms where other forms of life exist, perhaps fundamentally different from our understanding. Could there be intelligent beings in an alternate universe, or could different versions of Earth exist in those distant parallel realms? Theories abound about what life could be like in an infinite cosmos. Our exploration of the universe is not just a quest for answers but a reflection of who we are. The search for extraterrestrial life pushes the boundaries of exploration and knowledge, driving us to confront the very essence of existence. As we ponder our place in the cosmos, the next chapter will take us into the philosophical implications of the universe's mysteries and expand our horizons even further. As we zoom out from our understanding of the universe, we encounter a staggering revelation. The universe is not merely a collection of stars and galaxies, but a cosmic tapestry of vast structures weaving through the fabric of spacetime. Some of the largest galactic structures found in our universe are known as galactic filaments, vast threads of galaxies held together by gravity. These filaments create an intricate network across the universe. Observations from the Sloan Digital Sky Survey reveal that these filaments comprise approximately 80% of the universe's visible mass, stretching over hundreds of millions of light-years. One of the most fascinating aspects of these structures is their evolution. Starting from the moment of the Big Bang when the universe was hot and dense, small fluctuations in density eventually led to the clumping of matter. These clumps grew over billions of years, evolving into stars, galaxies, and massive galactic clusters. But how do we study these enormous cosmic structures? Astronomers often employ advanced telescopes and computer simulations, allowing them to predict the formation and evolution of the universe from the earliest moments to the present day. For instance, the Millennium simulation, completed in 2005, is one of the largest and most detailed simulations of the universe's evolution. It predicts galactic formations that closely match our observational data, painting a vivid picture of galactic structures emerging from the chaos of the cosmos. Yet, alongside the grandeur of these structures lies an unsettling truth: cosmic voids. These vast stretches of space contain far fewer galaxies than expected, raising questions about the universe's distribution of matter. For example, the Boötes void, often referred to as the Great Void, is an enormous cosmic void discovered in 1981 that contains very few galaxies, extending over 330 million light-years across. How did such a barren region come to exist amid the backdrop of our galaxy-laden universe? This question leads to deeper inquiries into the nature of dark matter and the early universe. Understanding these cosmic structures not only expands our comprehension of the universe's layout but also cements our place within it. The more we delve into these grand designs, the more we realize how interconnected all cosmic phenomena truly are. As we edge closer to the boundaries of the observable universe, we must confront the realities of matter distribution and consider what lies beyond these massive galactic filaments. Time and space, two foundations of our existence that intertwine in ways we continue to explore. From the very first moments after the Big Bang, space and time have been inextricably linked in a phenomenon we call spacetime. But what does this mean as we venture toward the edge of the observable universe? Einstein's theory of general relativity revolutionized our understanding of spacetime. It proposed that massive objects warp the fabric of spacetime, causing what we perceive as gravity. This means the universe is not just a vast expanse, it is a dynamic entity that behaves differently under various conditions. Consider black holes, regions of spacetime where gravity is so intense that nothing, not even light, can escape. The event horizon of a black hole presents a surreal perspective of time. As you approach a black hole, time slows down relative to an outside observer. This bizarre effect has led scientists to ponder, if time can behave differently within the confines of spacetime, what implications does this have for our understanding of the universe at large? The implications stretch into the realm of cosmology. As the universe continues to expand, the fabric of spacetime is itself stretching. This expansion is not merely the movement of galaxies away from each other, it suggests that space is being created between them. The rate of this expansion is driven by one of the universe's most enigmatic components, dark energy. Astrophysicists, through observations of distant supernovae, found that the universe is expanding at an accelerating rate. This discovery in the late 1990s was groundbreaking, leading to a re-evaluation of cosmic models. The precise nature of dark energy remains one of the universe's greatest unsolved mysteries. Will we ever comprehend how these forces dictate not just the fate of galaxies but the very fabric of time itself? As we take another step back, contemplating our universe's past and future trajectory, one question remains: can time itself be manipulated, or is it a linear path we are bound to follow? As we reach the edge of the observable universe, we must confront the limits of our knowledge and understanding, what lies beyond. The observable universe stretches about 93 billion light-years across, but that's just a fraction of what might exist beyond. The cosmic horizon marks the edge of what we can see, defined by the distance that light has traveled since the Big Bang. Beyond this horizon, there may exist regions of space forever out of our reach due to the expansion of the universe. It raises profound questions about the nature of reality. If the universe is infinite, can we ever truly know it? Some propose that there might be other universes existing beyond our observable limits, leading to theories of the multiverse. In these alternate universes, the laws of physics could operate differently, spawning entirely different realities. Imagine a universe where gravity pulls in the opposite direction, or where the fundamental constants of nature differ from our own. The idea is both thrilling and daunting, and it puts our existence into perspective, a mere speck in an endless cosmos of possibilities. But then again, how can we investigate such realms beyond our observational capacity? Scientists are developing methods to infer properties of these hidden areas through cosmic background radiation and gravitational waves. Moreover, the search for gravitational waves could reveal echoes of events from the universe's infancy, granting us insights into realms we can't directly observe. This hunt for information from beyond our observable universe holds immense promise for unveiling the mysteries of existence. As we close the chapter on the visible cosmos, we brace ourselves for a deeper question: can we ever break through the barriers of the observable universe? Having traversed through the structure and fabric of the universe, we now delve into the philosophical implications of what we've discovered. What does it mean for us to be part of this colossal cosmos? Philosophers and scientists alike have grappled with our place in the universe for centuries. The sheer scale of the universe, with its countless stars and galaxies, can evoke a sense of insignificance. Yet, it also inspires awe and curiosity about our existence. One of the key questions we must ask ourselves is, are we alone in the universe? The search for extraterrestrial life is not merely an astronomical endeavor, it has profound implications for our understanding of life itself and our role in the cosmos. Moreover, theories such as the anthropic principle suggest that the universe is fine-tuned for our existence. This raises the question, is there a purpose behind our existence, or are we just byproducts of cosmic events? The implications of our discoveries reverberate through various fields: science, spirituality, and ethics. For instance, the discovery of exoplanets in habitable zones amplifies the discussion about the uniqueness of Earth. If life exists elsewhere, it challenges long-held beliefs about human specialness and the narrative of creation. This, in turn, can lead to a reframing of our responsibilities as stewards of Earth and its biosphere. As we venture further into the unknown, we stir deeper questions. How might our understanding of the universe evolve as new discoveries are made? The convergence of science and philosophy continues to push boundaries, questioning not just our place, but also the very nature of reality itself. With each leap in knowledge, we redefine our understanding of existence. As we step back and reflect, we find that the universe is not just an infinite expanse but a mirror reflecting our quest for meaning and understanding. As we draw our journey to a close, we turn our gaze toward the future of cosmic exploration. What lies ahead for humanity as we continue to unlock the secrets of the universe? Advancements in technology are revolutionizing our ability to explore the universe. Space agencies like NASA and ESA are developing missions that will take us beyond the boundaries of our solar system, such as the upcoming James Webb Space Telescope, designed to capture the earliest light from the universe. This telescope will provide a deeper look into the formation of stars and galaxies, potentially offering insights into the conditions that fostered life. Moreover, private companies are venturing into space exploration, introducing new possibilities for research and development. SpaceX aims to revolutionize space travel, potentially making colonization of Mars a reality within the next few decades. This ambition raises challenges. How do we ensure ethical exploration beyond Earth? The implications of establishing a human presence on another planet could echo across generations, forcing us to consider our role as cosmic citizens. In addition to Mars, missions to icy moons like Europa and Enceladus are on the horizon, where the potential for finding alien life exists beneath their frozen surfaces. These explorations might not only answer whether we are alone in the universe but could redefine what we understand about life itself. As we push the boundaries of our exploration and knowledge, we are reminded of the importance of unity and collaboration on Earth. Our greatest achievements stem from collective efforts, transcending borders and cultures. The future of cosmic exploration is not just a quest for knowledge, it is a testament to our enduring spirit and curiosity. As we stand on the precipice of new discoveries, one question remains pressing: what truths will we uncover about our universe and ourselves? Will we find answers to the questions that have haunted humanity for millennia, or will we discover that the journey itself is just as important as the destination? As we conclude this exploration, let us carry forward our curiosity and wonder, for in the vastness of the universe, every answer breeds new questions, and every discovery deepens the cosmic mystery. As we delve deeper into the cosmic expanse, one question looms larger than any star: what lies beyond the cosmic horizon? The observable universe is merely a glimpse of a vast, intricately woven fabric of reality, stretching beyond the limits of our perception. Our cosmic horizon is determined by the speed of light, a fundamental constant that dictates the distance light can travel since the Big Bang. Today, we're about to embark on an exploration of the unknown, where the edges of our understanding meet the infinite possibilities of space. Consider this: the observable universe spans approximately 93 billion light-years across. But what does this mean? Every point in the universe expands outwards, pulling distant galaxies away from us, many of which we will never observe. This phenomenon isn't just a mathematical abstraction, it's a tangible reality shaped by the universe's expansion. The galaxies we see today are not the same as those we will observe in a billion years, as they drift further away, unreachable in the future due to the universe's relentless expansion. In our journey, we also contemplate the concept of the cosmic horizon, the threshold of our observable reality. Beyond this horizon lies an expanse that remains forever unobservable, shrouded in the mystery of time and space. Can any information escape this boundless void? The answer may lay hidden within the nature of light itself and how it interacts with the very fabric of space-time. To better illustrate this, let's look at the concept of cosmic inflation, a rapid expansion that occurred just after the Big Bang. This event set the stage for the universe's continued expansion and created the vast distances we see today. As a result, regions of space that were once close together are now separated by enormous distances, leading to the unobservable areas beyond our reach. Interestingly, some theorists propose that there are regions of space with different physical laws, a multiverse. Can you imagine? An infinite number of parallel universes, each with distinct properties and rules. What does this mean for our understanding of reality? These theories challenge the very essence of what we perceive as the universe, posing meaning-altering questions about what is beyond the cosmic horizon. What if our universe is merely one bubble in a sea of innumerable existence? Each theory invokes both wonder and skepticism, urging scientists to refine their understanding of our universe's edge. Some speculate about observable effects from other universes impacting us, albeit subtly. Is it possible that we, too, are influenced by these unseen realms? As we ponder these enigmas, we unveil the fragile underpinnings of our reality. The universe's complexity is a reflection of the questions we dare to ask. As we conclude this exploration of the cosmic horizons, we are left with a stark reminder: the universe is not merely what lies within our sight, it is also everything that exists beyond it. There are realms we may never comprehend, yet, this very mystery propels our quest for knowledge. And just when you think we've reached the brink of understanding, a new discovery illuminates yet another unfathomable question. What's truly out there remains one of the greatest mysteries yet to be solved. What new secrets does the universe hold just beyond our reach? The universe is expanding, a fact that has provoked both awe and confusion since it was first proposed. But what if I told you that the majority of this expansion is driven by something we don't even fully understand? This mysterious force is known as dark energy, making up about 68% of the universe. Discovered in the late 1990s through observations of distant supernovae, dark energy reveals one of the most shocking truths about the cosmos. It is not simply a relic of the Big Bang but an active component that shapes the universe's evolution. The implications of dark energy challenge our traditional views of gravity, space, and time. Imagine a universe where every galaxy you see is being pushed apart by a force you cannot see, like trying to walk through a dense fog. It's a daunting thought. Dark energy operates uniformly throughout space and grows stronger as the universe expands. This means that the forces holding galaxies together via gravity are increasingly outmatched by the relentless expansion dark energy enforces. One of the fundamental questions surrounding dark energy is its nature. Is it a cosmological constant, a fixed energy density of empty space, or does it vary? Some scientists propose the existence of quintessence, a dynamic form of dark energy that changes with time and space. The ongoing debate fuels research and experimentation, leading to a plethora of hypotheses and theories that ignite imaginations around the world. As we venture deeper into understanding dark energy, we also encounter peculiar paradoxes. One such example is the concept of cosmic acceleration. Evidence suggests that the universe's expansion is not just continuing but accelerating. This revelation raises crucial questions. How can this acceleration coexist with classical physics, which suggests gravitational attraction should decelerate expansion? One astonishing universe feature is the vast voids between galaxies, often seen as cosmic deserts. These regions can serve as a lens for understanding dark energy's role, as they appear more pronounced in a universe undergoing accelerated expansion. By studying these voids, astronomers gain insight into the distribution of dark matter and, ultimately, dark energy itself. Moreover, the gravitational effects of dark energy can lead to the fascinating possibility that it may shape the very structure of the universe, impacting galaxy formation and distribution. As we continually refine observational tools and techniques, we gain glimpses into the universe's structure, unveiling the roles dark matter and dark energy play in cosmic evolution. Exploring dark energy isn't merely an academic exercise, it resonates on philosophical levels as well. What does it mean for humanity's place in the universe if it is influenced by forces we cannot comprehend? As we push the boundaries of knowledge, we realize that dark energy might not just affect the cosmos, it can redefine our understanding of existence itself. As we conclude this chapter, we must ask ourselves, how will the unfolding story of dark energy impact our perspectives on the universe and the future of exploration? The answers may unfold as we continue our journey through the cosmos. In our quest to explore the universe, we often seek the remnants of its birth. The Big Bang, which happened approximately 13.8 billion years ago, marked the inception of space, time, and everything within it. But what if I told you we can still hear echoes of this monumental event today? These echoes come in the form of gravitational waves, ripples in space-time that reveal not only the universe's history but also its ongoing tale. Discovered in 2015 by the LIGO Observatory, gravitational waves opened a new frontier in astrophysics, allowing us to sense cosmic events beyond traditional electromagnetic observations. Imagine the drama, two black holes colliding, producing waves that traveled across the cosmos, eventually reaching Earth and providing us with a window into highly energetic phenomena. Each event captured unfolds a narrative about the universe, from the birth of stars to the collision of galaxies. These discoveries add depth to our understanding of gravitational physics, shining light on the entities that exist at the universe's edges. With the advancement of observational technology, we now have the potential to detect signals from the early universe itself. Gravitational waves could provide clues about the moments immediately after the Big Bang, particularly during cosmic inflation. Could we unravel the very nature of the forces set into motion during that cataclysmic event? The implications of this discovery reach beyond mere curiosity. They challenge our understanding of fundamental physics. For instance, the relationship between gravity and quantum mechanics remains one of science's greatest puzzles. By harnessing the insights from gravitational waves, we may uncover a reconciliation between these traditionally competing theories. This could reshape our very understanding of reality. To visualize the potential of gravitational wave astronomy, consider the vast array of cosmic phenomena it may help us explore. These include the mergers of neutron stars, events that could provide insight into heavy element formation, the nature of black holes, and even the potential existence of exotic celestial bodies. Each detection, each new gravitational wave signals the unfolding narrative of cosmic evolution. Moreover, as humans equipped with curiosity and intellect, we stand at the precipice of a new scientific era. Gravitational waves hold the promise of an unprecedented understanding of the universe's structure and dynamics, merging the science of gravity with the fabric of the cosmos. It's an invitation to explore themes that have long captivated humanity: the quest for knowledge about existence, creation, and the cosmos. As we reflect on the role of gravitational waves, we mustn't forget the bigger picture. Each wave we detect carries within it stories of a universe in constant flux, a dance of celestial bodies that intertwine in ways we are only beginning to fathom. What new revelations could we uncover as technology evolves, reaching further back into the echoes of time? In closing, gravitational waves remind us that the universe is not a static entity but a living, breathing tapestry woven from energy, matter, and time itself. As we listen closely, we begin to understand our place within this magnificent symphony. In the quest to understand the universe, telescopes have become our eyes in the sky, revealing mysteries that were once unfathomable. The evolution of telescopes has been pivotal in expanding our knowledge of cosmic phenomena, taking us from mere glimpses of distant stars to detailed observations of galaxies billions of light-years away. The first major leap came with the invention of the refracting telescope in the early 17th century. Galileo Galilei, armed with his handheld telescope, made groundbreaking discoveries, including the moons of Jupiter and the phases of Venus. These observations provided vital evidence for the heliocentric model proposed by Copernicus, challenging the long-accepted geocentric view of the universe. Fast forward to the present, and we have plunged deeper into the cosmos with advanced telescopes like the Hubble Space Telescope. Launched in 1990, Hubble has provided breathtaking images and data that have significantly altered our understanding of the universe. One of its remarkable contributions has been in measuring the rate of expansion of the universe, a key factor in cosmology. Hubble's observations of distant supernovae led to the shocking discovery that the universe is not only expanding, but the rate of expansion is accelerating. This unforeseen revelation hinted at the existence of dark energy, a mysterious force that is counteracting the gravitational pull of matter in the universe. As technology has advanced, so too have our telescopes. The upcoming James Webb Space Telescope promises to push the boundaries even further, allowing us to peer into the dusty regions of space where new stars are born. However, each leap in technological capability brings its own questions and mysteries. For instance, how do we interpret the vast amounts of data collected by these telescopes? The challenge lies not only in capturing images but in understanding what they tell us about the formation of galaxies, stars, and the universe's evolution. Hubble's deep field images, capturing thousands of galaxies in seemingly empty patches of sky, serve as a stark reminder of how much we have yet to learn. Furthermore, the limitations of these observatories create a sense of wonder. While they can observe objects billions of light-years away, they are limited by the speed of light and the observable universe's constraints. How much more lies beyond, hidden from our view? This chapter highlights the tension between discovery and limitation, as each telescope reveals new wonders while simultaneously reminding us of the vast unknown still waiting to be explored. As we look toward the future, we must prepare for both the answers that new technologies will provide and the questions they will pose. With telescopes like the Vera C. Rubin Observatory soon to be operational, we stand on the brink of a new era in astronomy. It will survey the night sky, capturing changes over time and, hopefully, revealing new cosmic secrets. In essence, each telescope serves as a bridge, connecting us to the universe's distant edges, reminding us of our small yet profound place in this cosmic tapestry. What lies beyond the limits of our current instruments? As we continue to innovate and explore, the universe may still hold secrets that challenge our very understanding of existence. Deep in the fabric of our cosmos lies a remnant from the birth of time itself, the cosmic microwave background radiation, or CMB. This faint glow fills the universe and is a crucial piece of evidence for the Big Bang theory, providing a snapshot of the universe when it was merely 380,000 years old. But what does this radiation really tell us about the universe and its origins? Discovered accidentally by Arno Penzias and Robert Wilson in 1965, the CMB was initially an enigma. The pair was trying to eliminate noise from their radio antenna experiments when they stumbled upon a persistent background signal. What they found was the afterglow of the Big Bang, a remnant thermal radiation that has been cooling ever since its inception. This radiation is isotropic, meaning it is uniform in all directions, but it also displays tiny fluctuations that reflect the initial density variations in the early universe. These fluctuations laid the groundwork for the distribution of galaxies and structures we see today. Detailed analysis of the CMB has led to groundbreaking insights into fundamental cosmological parameters, such as the universe's age, composition, and rate of expansion. The Planck spacecraft, which surveyed the CMB from 2009 to 2013, provided a wealth of data that refined our understanding of these critical aspects. According to its findings, the universe is approximately 13.8 billion years old, composed of about 68% dark energy, 27% dark matter, and only 5% ordinary matter. These revelations have profound implications. They challenge us to reconsider the nature of existence and the building blocks of reality. If ordinary matter constitutes such a small fraction of the universe, what is dark matter really? And what about dark energy? What force is driving the accelerated expansion we observe? The quest to decode the CMB continues to inspire scientists worldwide. Current research aims to uncover more about the universe's infancy, seeking answers about inflation, the rapid expansion of the universe in its first moments. What triggered inflation, and how did it shape the universe's large-scale structure? As we push the boundaries of observational techniques, new discoveries about the CMB may hold the key to understanding phenomena that currently elude us. The fluctuations in the CMB also suggest regions of gravitational waves that could provide insights into the nature of the universe's expansion. The CMB serves as a cosmic tapestry that weaves together the past and future, bridging our understanding of creation and eventual destiny. As we dive deeper into the mysteries of the universe, the CMB invites us to ponder our place within it, igniting a sense of wonder about what lies beyond what we can currently comprehend. As we explore the universe and uncover its secrets, profound philosophical questions emerge about our existence, purpose, and the nature of reality itself. The discoveries made at the edges of the observable universe challenge our understanding and invite us to rethink our place in the grand cosmic scheme. One of the most pressing questions is whether we are alone in the universe. The search for extraterrestrial life has intensified as we discover more about potentially habitable exoplanets. The sheer number of planets in our galaxy alone, estimations suggest as many as 100 billion, opens the door to possibilities beyond our imagination. What if we were to encounter intelligent life? How would such a discovery affect our understanding of ourselves and our philosophical frameworks? Would life in other galaxies follow similar evolutionary paths as we did, or could it take entirely different forms? The discovery of microbial life on Mars or the intriguing conditions of Europa's subsurface ocean could ignite profound shifts in our perception of life's resilience and adaptability. Additionally, the implications of multiverse theories, suggesting that other universes may exist with different physical constants and laws, prompt us to question the uniqueness of our universe and our existence. If our universe is but one of many, could each universe harbor its own intelligent civilizations? The philosophical implications extend to our understanding of time and space, as science reveals that our perception might be limited to our human understanding. As we delve into the nature of black holes and the fabric of space-time, we grapple with concepts that blur the lines between science, philosophy, and even spirituality. The study of black holes challenges our understanding of causality and the ultimate fate of information. Can information be destroyed? If so, what does that mean for the reality we perceive? These questions can lead to existential reflections. As we explore the universe, we realize that the act of knowing may be intertwined with a deeper, possibly spiritual understanding of our existence. The vastness of the cosmos evokes a sense of humility, a reminder of our smallness compared to the grandeur of the universe. As we reach the limits of observation, we encounter not only the physical boundaries of the observable universe but also the philosophical boundaries of understanding. Each discovery at the edges of the cosmos invites us to reconsider long-held beliefs, pushing the limits of knowledge and understanding. As we stand at the brink of the unknown, we must embrace the uncertainties and allow them to inform our philosophical outlook, recognizing that the pursuit of knowledge may forever be intertwined with the mysteries of existence. In conclusion, exploring the philosophical ramifications of cosmic discovery enriches our journey through the universe, reminding us that each question raised leads us further into the depths of knowledge and understanding. As we gaze into the depths of the cosmos, we face an intriguing dilemma. The universe is expanding, and this expansion affects how we perceive its very edges. The observable universe is defined by the distance light has traveled since the beginning of time, giving us a cosmic horizon that delineates what we can see from Earth. This horizon, however, is not static. It is constantly shifting, each moment granting us new glimpses of the universe, while simultaneously pushing parts of it beyond our reach forever. Understanding the concept of the cosmic horizon requires a dive into the very fabric of space and time. Imagine a balloon being inflated. The surface represents the universe, and the dots on the surface represent galaxies. As the balloon expands, the dots move away from each other. This simple analogy illustrates the expansion of our cosmos, but it also hints at a deeper mystery. Where does this expansion end? What lies beyond what we can observe? To find answers, scientists have studied the redshift of galaxies, an effect caused by the stretching of light as galaxies move away from us. The light from distant galaxies shows a shift towards the red end of the spectrum, indicating they are receding. This shift is not just a measure of distance but a key to understanding the rate of the universe's expansion. In recent years, the rate of this expansion has led to debates among cosmologists. Discrepancies in measurements have sparked discussions about the nature of dark energy, the mysterious force driving this accelerated expansion. Dark energy makes up about 68% of the universe, yet remains one of the greatest mysteries in science. Could what lies beyond our observable universe hold the answers to these questions, or are we forever confined to a limited perspective? Perhaps the expansion itself harbors the enigma, an ever-increasing distance between us and the unseen realms of the cosmic unknown. As we peer into the abyss, the horizon teases us with the promise of discovery. Will we one day breach that cosmic boundary, and if so, what truths will await us? Through the lens of the cosmic horizon, we must also grapple with a profound thought. If there are regions beyond our observable universe that are forever unreachable, What does that mean for our understanding of existence, time, and space? The idea of an infinite cosmos can be exhilarating and daunting, forcing us to confront the limits of human understanding and the vastness of creation. We might stand on the brink of unimaginable truths or profound mysteries that are simply beyond our grasp. And yet, this quest for knowledge, this unyielding desire to understand, is what drives humanity forward. We may never know what lies beyond our horizon, but the journey of discovery is a testament to our spirit. Buckle up as we continue our voyage into the cosmos, where each revelation only deepens the mystery. What are the philosophical implications of our findings? Dark energy is a term that sends shivers down the spine of scientists and enthusiasts alike. Making up an astonishing 68% of the universe, it remains one of the most elusive components of modern cosmology. But what does it mean for the future of the universe? The story of dark energy began in the late 1990s with observations of distant supernovae. Scientists discovered that these exploding stars were dimmer than expected, suggesting they were farther away than initial models predicted. This led to the shocking conclusion that not only was the universe expanding, but it was doing so at an accelerated rate. How could this be? Traditional physics couldn't account for such a phenomenon. The unraveling began with the introduction of the cosmological constant, a concept initially proposed by Albert Einstein as a means to allow for a static universe. In hindsight, this constant was intended to balance out the force of gravity, but circumstances changed once it was discarded in favor of a dynamic cosmos. Fast forward to today, and it appears dark energy has re-entered the conversation, leading to new theories that could forever change how we perceive the universe. Scientists propose several hypotheses about dark energy, each with its own implications for understanding the cosmos. One such theory suggests it could be a property of space itself, an intrinsic energy inherent in the fabric of space that drives galaxies apart. Alternatively, there are ideas suggesting it might be related to the energy of quantum fields. What if the laws of physics are incomplete? What if our grasp of forces in matter requires a fundamental revision? As we explore dark energy, we might encounter unexpected revelations, and one question looms large: how will it shape the fate of the universe? The accelerated expansion could lead to a big freeze, where galaxies drift apart, stars dim, and the universe experiences an eternal twilight. On the other hand, could dark energy evolve over time or even lead to a collapsing universe? Such ideas are exhilarating and terrifying, compelling us to confront our place in the cosmos. As we dive deeper into dark energy, we'll uncover more mysteries that challenge our understanding of existence. The implications for future cosmic exploration and the human experience are vast, making this one of the most thrilling fields of modern astrophysics. How far can we push the boundaries of our knowledge? Each discovery tantalizes, reminding us that the universe is a complex web of interconnections, each thread contributing to the rich tapestry of existence. The quest for understanding dark energy is not just scientific, it is existential, urging us to keep asking those eternal questions: what is reality? What lies ahead as we journey through this cosmic landscape? In 1916, Albert Einstein laid the groundwork for one of the most profound theories in the world of physics, general relativity. Einstein posited that massive objects warp the fabric of spacetime, creating gravitational waves. These waves are ripples in spacetime that occur when massive celestial bodies, like black holes or neutron stars, collide or orbit each other. For decades, these waves remained a theoretical prediction, until March 2016, when the LIGO Observatory made the groundbreaking announcement: they had detected gravitational waves from colliding black holes. This event was a monumental leap in our understanding of the universe, opening up an entirely new field of astrophysics, gravitational wave astronomy. But what do gravitational waves have to do with the observable universe? These ripples in space-time can offer profound insights into the very early moments following the Big Bang. Researchers theorize that during those first moments, massive fluctuations occurred, generating waves that might still echo throughout the cosmos today. By detecting and studying these cosmic ripples, scientists could potentially glean valuable information about the conditions that existed in the infancy of the universe. This adds a layer of depth to the ongoing quest to understand how the universe expanded and evolved. Could these echoes hold the key to understanding dark matter and dark energy? What other secrets about the universe's origins might they reveal? As we explore the implications of gravitational waves, we'll discover how they have the potential to reshape our understanding of the cosmos. Each detection is like a note in the symphony of the universe, providing clues about its composition, structure, and fate. With every observation, we peel back the layers of cosmic history, moving beyond mere images of galaxies and phenomena, and entering a realm where sound waves travel through the very fabric of existence. Each breakthrough in gravitational wave astronomy not only enhances our cosmic knowledge but also pushes the boundaries of what we believe is possible in science. The implications are immense, and the questions remain: how much more can we learn from the universe's echoes, and what does it mean for our understanding of existence? As we navigate this exciting frontier, we face a remarkable reality, one where the fabric of spacetime reveals the deepest mysteries of the universe. Let us continue our exploration to uncover more of these cosmic secrets that hide in the fabric of reality. The universe stretches beyond what we can see. The observable universe, limited by the distance light has traveled since the dawn of time, is a mere fraction of the cosmos. But what lies beyond? To truly understand our place in this vast expanse, we must first unravel the beginnings of infinity. The concept of infinity is daunting. It raises more questions than answers. Imagine a space so vast that it dwarfs our entire understanding of existence. Our journey begins with the Big Bang, a colossal explosion that birthed everything we know approximately 13.8 billion years ago. The remnants of that event are still observable today through the cosmic microwave background radiation, which permeates the universe and serves as a window into its earliest moments. The universe, after the Big Bang, began expanding rapidly. This expansion is not just a moving apart of galaxies, it's the very fabric of space itself that is stretching. So, as we gaze into the night sky, we are, in fact, looking back in time, seeing the universe as it was millions or even billions of years ago. The light from distant stars that reaches us today began its journey long before humans walked the earth. Every glimmering in the sky is a historical record, their light tells a story locked in time. But the question lingers: what lies beyond these twinkling lights? The universe comprises billions of galaxies, each swirling with countless stars, planets, and potential for life. The sheer scale is mind-boggling. The Milky Way galaxy alone contains an estimated 100 to 400 billion stars. But this is just one of the estimated 2 trillion galaxies. Each galaxy is a vast city of stars, yet we've hardly begun to explore even our own. As we delve deeper into galactic structures, we begin to glimpse the possibilities of what may exist beyond the observable universe. Could there be other systems, very different from ours, possibly harboring life? Scientists have launched missions to search for exoplanets within habitable zones around distant stars. These discoveries raise profound questions about our place in the cosmos. The potential for extraterrestrial life challenges the very notion of what it means to be alive in this universe. Perhaps, beyond our reach, intelligent civilizations gaze skyward, wondering the same about us. As we continue to explore and expand our knowledge, we discover that the beginning of infinity is just the start of our cosmic journey. In the next chapter, we'll dive deeper into the measurement of cosmic distances, a critical aspect that helps astronomers gauge the scale of the universe and our position within it. But first, let's ponder, what if our universe is just one of many? What if, Beyond what we perceive, there exists an infinite multiverse, stretching across dimensions we can barely comprehend. The adventure is just beginning. As we embark on this cosmic exploration, one of the most essential tools in our celestial toolkit is the measurement of cosmic distances. How do we quantify something so vast, so seemingly immeasurable? Understanding distances in space is fundamental to comprehending the structure of the universe and our position within it. Astronomers use a series of ingenious methods, beginning with parallax. This technique relies on observing the apparent movement of nearby stars against the background of more distant stars as Earth orbits the Sun. This effective distance measurement for stars within about 100 light-years illustrates the elegance of simple geometric principles applied across the cosmos. However, as we look farther, the distances become immense and complex. For stars beyond parallax range, astronomers rely on other methods, such as standard candles, particularly Cepheid variable stars. These stars vary in brightness at predictable intervals, allowing scientists to determine their distance based on luminosity. This method has been pivotal in establishing the distance scale of the universe. On a grander scale, we utilize redshift, the phenomenon where light from distant galaxies shifts toward the red end of the spectrum as they move away from us. This not only reveals the motion of galaxies but also provides insight into the universe's expanding nature. The farther a galaxy is, the faster it appears to be receding. This observation forms the cornerstone of Hubble's law and demonstrates that the universe is not static but dynamic. Using these measurements, astronomers estimate that the observable universe is about 93 billion light-years in diameter. But what about the portion of the universe beyond our observational limits? Does it continue indefinitely? The mere thought sends shivers down our spines, the possibility of realms never to be seen, galaxies forever out of reach. This journey of measurement becomes even more crucial when we consider cosmic expansion driven by dark energy. Scientists grapple with this mysterious force responsible for the acceleration of the universe's expansion. Understanding distances aids in quantifying the effects of dark energy, leading to profound implications about the universe's fate. As we really ponder these ideas, we might find ourselves confronted with existential questions. How does our small blue planet fit into this grand cosmic tapestry? What does our existence mean in light of such vastness? The depth of inquiry becomes infinite, much like space itself. Our understanding of distances might shape our perceptions of life and the universe, but it does not stop here. Next, we will explore the cosmic microwave background radiation, a remnant of the Big Bang, which offers an image of the universe just 380,000 years after its inception. What does this early snapshot reveal about the universe's formation and evolution? Join me as we uncover the mysteries lurking within this ancient light. The universe is teeming with radiation, yet one type holds the key to our understanding of cosmic origins, the cosmic microwave background radiation, often abbreviated as CMB. This ancient light is a relic from the early universe, a snapshot of the cosmos approximately 380,000 years after the Big Bang. But what does that mean for us today? Picture the universe as a hot, dense plasma filled with photons, electrons, and protons just after the Big Bang. As it expanded, the temperature began to drop. Essentially, the universe cooled down, allowing electrons and protons to combine and form neutral hydrogen atoms. This moment, known as recombination, marked a significant shift. Photons were free to travel across the universe, and what was once a dense fog transformed into a clear cosmos. The CMB is the afterglow of that event. It pervades the universe, filling every corner, and can be detected today as a faint glow. In fact, the CMB is nearly isotropic, meaning it is uniform in every direction we look, with tiny fluctuations that hint at the seeds of all future structures, galaxies, stars, and planets yet to come. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson was monumental. They stumbled upon this pervasive microwave radiation while working on a satellite communication project. Dismissing it as noise at first, they realized they had uncovered evidence supporting the Big Bang theory. This serendipitous moment changed our understanding of the universe forever. Since then, observational missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have measured the CMB with astounding precision. These missions have provided critical insight into the universe's age, composition, and the rate of its expansion. The data collected reveals that the universe is about 13.8 billion years old and provides constraints on the proportions of dark matter and dark energy in our cosmic makeup. One of the most profound implications of studying the CMB is its role in confirming inflation theory, a brief, exponential expansion that occurred just fractions of a second after the Big Bang. These ideas challenge our understanding of time and cosmic geography, leading us to question the very nature of reality. What lies beyond our observable universe? Could there be other regions undergoing similar processes but in ways we can't yet fathom? As we peel back the layers of the CMB, we draw closer to understanding not just the universe but our purpose within it. But what of the dark matter and dark energy that shape our universe? Next, we will explore these enigmatic components that govern cosmic behavior and structure. Are they mere figments of our imagination or the very fabric of reality? The mysteries deepen. As we delve deeper into the cosmos, we encounter two of the universe's biggest mysteries: dark matter and dark energy. Together, they constitute about 95% of the total composition of the universe, yet their nature remains elusive. What are dark matter and dark energy, and how do they affect our understanding of the cosmos? First, let's discuss dark matter. Observations of galaxies reveal that the visible matter we can see, stars, gas, dust, makes up just a fraction of the mass needed to hold galaxies together. This discrepancy leads scientists to propose the existence of dark matter, an unseen substance that does not emit, absorb, or reflect light. It interacts with regular matter via gravity, and its presence is inferred from gravitational effects. Think of it as a ghostly anchor, holding galaxies in place while remaining invisible. Evidence of dark matter comes from various observations, including the rotation curves of galaxies. As galaxies rotate, stars at the edges move at speeds that suggest there must be additional unseen mass. Without it, galaxies would tear themselves apart. This led physicist Vera Rubin to champion the dark matter hypothesis in the 1970s, as she meticulously documented these anomalies. Today, experiments to detect dark matter particles directly continue, often utilizing large underground detectors or particle accelerators, but so far, it remains as elusive as ever. On the other hand, dark energy is a more perplexing enigma. Discovered in the late 1990s, dark energy is the force behind the universe's accelerated expansion. Observations of distant supernovae revealed that instead of slowing down due to gravity, the expansion of the universe was speeding up, prompting questions about what could cause such behavior. The leading theory proposes that dark energy fills space uniformly and acts as a repulsive force. This mysterious force is often associated with the cosmological constant, a concept introduced by Einstein over a century ago, which he later dubbed his greatest blunder when he abandoned it in favor of a static universe model. Despite extensive efforts, understanding dark energy poses significant challenges. Many researchers speculate whether we might need a new physics framework altogether. What if our current laws of physics cannot account for the universe's behavior? As we stand at this intersection, we contemplate profound implications for our understanding of reality. Dark matter and dark energy force us to rethink our concepts of gravity, time, and the universe's fate. In the next chapter, we will explore the tantalizing question of extraterrestrial life. Is Earth alone in this vast universe, or could we find other sentient beings gazing into the cosmos, pondering the same questions we are? Strap in as we embark on this quest for life beyond Earth, a journey filled with wonder, discovery, and potentially shocking revelations. As we navigate the cosmos, one question rises above all others: are we alone? The search for extraterrestrial life has captivated humanity for centuries, driving us to peer into the starry skies and seek answers among the stars. Scientists are now using advanced technologies and methodologies to explore this profound question in depth. The search begins in our solar system, our nearest celestial neighbors. Mars, with its dry riverbeds and polar ice caps, holds tantalizing evidence of past water. Missions like Curiosity and Perseverance seek clues that could indicate life once flourished on the red planet. Recent discoveries of subsurface lakes on Mars reinforce the possibility of microbial life still existing beneath its arid surface, igniting imaginations and fueling future exploration. But Mars is just the tip of the iceberg. The icy moons of Jupiter and Saturn, such as Europa and Enceladus, harbor oceans beneath their frozen crusts. Scientists speculate that these hidden oceans could provide the necessary conditions for life to thrive. NASA plans to send future missions to probe these moons, searching for signs of life, whether through biosignatures or even sampling the material that erupts into space through geysers. The idea that life could exist in these extraterrestrial oceans stirs excitement and hope. Beyond our solar system, astronomers have identified thousands of exoplanets, planets orbiting distant stars, through missions like Kepler and TESS. Among them, a subset lies in the Goldilocks zone, not too hot, not too cold, just right for liquid water. The more we discover, the more intriguing possibilities arise. Could these distant worlds host intelligent beings gazing back toward Earth? The quest for alien life comprises scientific rigor and speculation. The Search for Extraterrestrial Intelligence (SETI) project utilizes powerful radio telescopes to scan the cosmos for extraterrestrial signals. Despite decades of monitoring, silence prevails, a cosmic quietude that's both eerie and bewildering. Are we simply not listening in the right way, or do we inhabit a lonely corner of the galaxy? Another approach is to consider life forms that may not resemble us in the slightest. The myriad forms of life on Earth, from extremophiles in boiling hot springs to bioluminescent jellyfish, demonstrate life's remarkable adaptations. If life can thrive in extreme conditions on Earth, it opens the door to possibilities far beyond our imaginations. What if life exists in gaseous forms, or as silicon-based entities, or even as non-corporeal intelligence? The prospect of extraterrestrial life has philosophical implications that challenge our understanding of existence itself. Exploring the universe in search of these beings places humanity at the center of an epic narrative about curiosity, exploration, and connection. What would first contact look like? What role do we play within a cosmic community? As we ponder these questions, we will soon turn to the grand cosmic structures that populate the universe. What remarkable formations beyond the stars define the celestial landscape? Get ready to uncover the wonders that comprise the vast framework of our universe. As we transcend the limits of individual galaxies and probe the vast architecture of the cosmos, we encounter the mesmerizing tapestry of great galactic structures. The universe is not just a collection of isolated galaxies, it is a web of interconnected filaments and voids, forming one of the most breathtaking landscapes imaginable. At the center of this cosmic dance are galaxy clusters. These colossal formations host hundreds or thousands of galaxies bound together by gravity. The Virgo cluster, for example, comprises over 1,300 galaxies and serves as a prime example of the intricate structures our universe holds. Observations suggest that clusters are continually merging, evolving, and reshaping the gravitational horizon. Beyond clusters, we encounter superclusters, massive groupings of galaxy clusters that span hundreds of millions of light-years. The Laniakea supercluster, which contains the Milky Way, is one such entity. It is a vast home to approximately 100,000 galaxies, demonstrating how interconnected our universe truly is. One must wonder, what larger structures loom beyond our supercluster? The cosmic web illustrates an even more grand design. This web of dark matter serves as the scaffolding for visible matter, guiding the formation of galaxies and galaxy clusters. Filaments of galaxies stretch and intertwine, with vast empty voids in between. The conception of this cosmic web offers a glimpse into the universe's underlying architecture, a grand design that seems almost intentional yet is born from the interplay of cosmic forces. The discovery of these cosmic structures reshapes our understanding of the universe. They reveal insights into the evolution of the universe and its large-scale dynamics, offering essential data to test theories of cosmology. But what forces drive this dizzying structure? Dark matter and dark energy play pivotal roles, shaping the way galaxies interact and evolve. As we uncover the intricate details of galactic structures, we are compelled to question our place within the cosmic hierarchy. Are we just one tiny planet amidst a vast horror of intergalactic relationships? The metaphorical distance between galaxies offers a humbling perspective. Each cluster is a fleeting moment in the timeline of existence. And yet, within this improbability, the essence of humanity perseveres. Next, we will journey through the nature of time and space. How are they connected to the universe's fabric, and what mysteries lie hidden within their relationship? Prepare yourself for a mind-bending exploration. As we venture deeper into the cosmos, our exploration leads us to one of the most profound questions humanity has contemplated: the nature of time and space. These two concepts are at the very core of our understanding of the universe, shaping the rules that govern everything from the motion of planets to the flow of light across the cosmos. In classical terms, time is seen as a linear progression, moving from the past through the present and into the future. However, Einstein's theory of relativity shattered this traditional view, intertwining time with space to form a four-dimensional continuum known as spacetime. According to this theory, the fabric of spacetime is curved by mass, and this curvature influences the movement of objects. Picture the universe as a vast sheet of fabric with heavy objects like stars and planets creating dips, causing nearby lighter objects to roll towards them. This insight revolutionized our understanding of gravity, not merely a force but a consequence of spacetime geometry. When we observe gravitational waves, ripples in spacetime created by massive accelerating bodies, we witness the very fabric of the universe in motion. Furthermore, relativity introduces the concept of time dilation, where time can elapse at different rates depending on an object's relative velocity or gravitational field. This means that someone traveling at near light speed would experience time differently than someone at rest. Time becomes fluid, challenging our instinctive perception of permanence and continuity. As we consider the relationship between time and space, we confront the implications for our understanding of the universe's evolution. The Big Bang marked not just the creation of matter but the inception of space and time itself. As the universe expands, questions of its ultimate fate arise. Is it an endless cycle of expansion and contraction, or will the universe inevitably reach a climax, a big freeze or a big crunch? As we grapple with these concepts, we find ourselves pondering the philosophical implications. What does it mean for existence if time is not a constant but an experience shaped by perspective? Could our understanding of time influence how we perceive consciousness and reality itself? The more we explore, the more we realize that time and space are not merely backdrops for the cosmic drama but integral characters in the unfolding narrative of the universe. In our next chapter, we will approach perhaps the most tantalizing aspect of cosmology, the edge of the observable universe. What lies beyond what we can see, and how does this shape our understanding of existence? Prepare for an exploration that challenges the very limits of our imagination. At last, we arrive at one of the most tantalizing frontiers in cosmology, the edge of the observable universe. Picture this, an ever-expanding balloon, where every point represents a galaxy. As the balloon inflates, the distance between points increases, mirroring the way our universe has been stretching since the Big Bang. But just how far can we see? The observable universe extends approximately 46 billion light-years in every direction, creating a cosmic sphere with a diameter of about 93 billion light-years. However, what lies beyond this observable horizon? The truth is, the universe continues far beyond our perception, potentially infinitely. As light from distant galaxies travels through space, it takes time to reach us. When we observe distant galaxies, we see them as they were long ago, not as they are today. Some galaxies may have long since ceased to exist, their light merely taking its time to arrive. The edge of the observable universe is not a physical barrier. Instead, it represents the limit of our observational capacity. Beyond this threshold, cosmic inflation might be weaving a fabric of galaxies and phenomena that we could never fathom. The laws of physics as we know them may no longer apply in ways we can understand. What kind of wonders or horrors lie beyond the veil of our limited perception? Astronomers speculate that the universe may harbor regions where the fundamental constants differ, creating universes where the laws of physics do not hold the same sway as they do in our own. The notion of a multiverse, an infinite ensemble of universes, each with its own unique properties, sparks both imagination and scientific inquiry. Could life exist in forms and conditions radically different from the ones we recognize? Furthermore, the edge of the observable universe raises philosophical questions that challenge human thought. If our universe is just one of many, does that diminish our significance? Are we mere specks in an infinite cosmic landscape? Or does it enhance our understanding of connection and existence? Perhaps we are part of a greater cosmic community, all striving to comprehend the mysteries of reality. As we conclude our exploration of the observable universe's edge, we find ourselves grappling with profound questions. What does it mean to be human in a universe so vast and complex? How do we fit into the grand story of existence? The more we explore, the more we realize that our search for knowledge is a never-ending journey, one filled with awe and wonder, forever pushing at the boundaries of our understanding. In our next chapter, we will delve into the philosophical implications of our cosmic discoveries. As we piece together this cosmic puzzle, what does it mean for humanity and our understanding of existence? Prepare for a thought-provoking discourse that will reshape our perception of ourselves and our place in the universe. As we stand on the precipice of understanding the universe, we encounter profound philosophical questions that arise from our cosmic inquiries. The discoveries we've made challenge our beliefs about existence, purpose, and intelligence itself. What does it mean to be human in a universe so vast and complex? From ancient times, philosophers have pondered the nature of existence, asking, why are we here? The answers have ranged from spiritual interpretations to scientific inquiries. With the advancements we've made in understanding the cosmos, we are forced to confront the limits of our current beliefs and understandings. The enormity of the universe often evokes a sense of insignificance. When we consider our small blue planet, suspended in the vastness of space, is it possible to maintain a sense of purpose? Are we mere accidents in an indifferent cosmos? Or does our consciousness imbue the universe with meaning, elevating our place within it? The philosophical implications extend beyond individual significance, they encompass ethical considerations as well.